Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Michael is here from the Hebrew University, and he's going to be talking to a few of us today. And if anybody else who's not on his schedule would like to talk with him, I think we can probably push the schedule out by an hour or so. So please tell me. Okay. Oh, and what is your topic, Michael? And there's Yuval.
There's Yuval. Just in time.
Just in time. We were calling you, waiting for you. Okay.
So it's going to be about upcrossing inequalities and stationary processes.
Upcrossing.
Okay,
it's going to be about upcrossing inequalities and stationary processes.
So, thank you for having me. And so no, they said it would screw up the
Okay.
the photography, but you can see, I think. I can write, if I write too small, just tell me and feel free to interrupt. So, let me first explain what upcrossings are.
Wait 1 minute.
Can you hear me? Is that okay?
The mic isn't to amplify your voice in the room.
I know. Well, the technician said I'd be on anyway, so.
Okay. So these might help a little better.
Oh, there's an eraser. Oh,
Yeah, well,
pens.
but these are new sets of pens. So first of all, you have different colors, and
Right, okay.
you should throw out all the old pens.
It seems to be working.
Well, okay.
Okay, so what is so what are upcrossings? So suppose we have just a real valued sequence of numbers. Okay, and we have an interval st. Right? And so we can draw it like this. We have our sequence, and we have, maybe I'll do it in a different color. We have s and t. So this is s, and this is t, and these are the x's. This is x1, x2. So an upcrossing of s and t by the sequence means two indexes, like maybe x2 and x5 in this case, where they go from below s to above t. That's all it is. You can define a downcrossing similarly.
Does it be necessarily direct, or can it do in between whatever it wants?
It doesn't matter. It doesn't matter. It's just a pair of elements in the sequence, which one is under s, and then sometime later we have an element over t.
But it could have crossed over t before, not.
It could have. It could have. And so we'll say that it has k upcrossings, means that there's some sequence of indices I1 less than J1 less than I2 less than J2 and so on, k pairs of indices such that xk, not xk, x im is less than s and xjm is greater than t for m from 1 to k. So it means that we do this k times, and as you said, it doesn't have to be, you don't have to necessarily take the immediate guy after it. So you might, here we have in fact 2, but I've just drawn 1. It also has 1. You can define the maximal number, it's not so important. And we say it has infinitely many upcrossings if it has infinitely many upcrossings. Okay, so easy, it's obvious that the limit of xn exists as n goes to infinity if and only if for every pair s and t, the number of upcrossings of s and t, of the interval st, is finite. This is just because in the extended sense. If the sequence is bounded, then this is also in the strict sense. Yeah, so this is just because the upper and lower limits are different exactly when you have infinitely many crossings of some interval. And so this has been for a constant sequence. And if we look at random variables, then we have essentially the same thing, only you have to qualify it and say almost surely. So the limit will exist almost surely if and only if for every s less than t, almost surely the number of upcrossings of st is finite. Okay, so you simply restrict yourselves to rational s and t, and then you have countably many events, and you intersect, and this is very, I think this is clear. Now, so what's the point? So if it's equivalent, why even be interested in this? So it's true, it's not interesting for an individual sequence, but when you have a convergence theorem which holds for a large class of sequences, what can happen is that proving this implies convergence, but also gives more information in some cases. So let me give the classic example. So suppose that xn in L1 is a martingale. Right, so that just means that, I'm sure everyone knows, but then one of the ways that you can prove that the sequence converges, there are several proofs, but one of them is Dub's inequality. Yeah, I have a sequence of random variables. Yeah. Well, it's an increasing. Stock isn't actually going to be about martingales, but so the Dub's inequality says that the probability that for every s and t, the probability that x1 to xn, well, probability that the infinite sequence crosses s and t k times is bounded by, well, this should be right, by the L1 norm of x over k t minus s. And so in particular, the probability that it crosses infinitely often is 0. So this implies convergence. But the pleasing thing about this is that you don't, the decay of the number of upcrossings doesn't really depend on the process. There's only this normalizing factor, which is the L1 norm, which you can't avoid. I mean, that has to be there. And other than that, it's independent of the process. And of course, you can't do better. Well, you could formulate other effective theorems possibly, but there is no universal rate of convergence for martingales. So you're not going to get anything which is
But this is an upper bound, then.
It's an upper bound. I think it's tight, but and it doesn't. Of course, it doesn't give you anything about the rate of convergence. You can be very far away from the limit for a long time and then dip down. So it's not a substitute, but it does give you something. So here's another example. This is Bishop in, I think, 65. So Bishop was interested in the ergodic theorem. So suppose that, so Zn is a stationary R-valued process. And we look at the time averages. So xn is the average of Z1 to Zn. Then Bishop proved exactly the same thing. Let's call this star. So star is true. Of course, Zn should be in L1. And again, all the same remarks apply. You don't have rates of convergence in general for the ergodic theorem, but this gives you some information about how the averages approach the limit. And again, the rate does not depend on the process beyond this normalizing factor. Now, recently there have been some improvements of these results. So for the martingales, there's a theorem by Dubins, Lester Dubins. Well, that's not recent. Yeah, that's an old result. It's from the 70s, I think. I don't remember the date. He showed that for bounded martingales, or non-negative, I think, is enough. I better not say that. Let's say bounded. The decay of these probabilities is exponential and depends only on S, T, and the infinity norm of x1. And so this was in the 70s, and then much more recently, still a few years ago, but in the late 90s, there was a sequence of results essentially proving the same thing as Bishop, but for non-negative processes. And again, you can get exponential decay. So Ivanov published this in 97, and then in 98 there was a paper by Jones, Kaufman, Rosenblatt, and Weirdo, and then in 99 there was a paper by Calico and Weiss, so I'm a little bit biased, but the history that I know for this paper is that the work was actually done in 92. I don't know, I didn't get the inside story from the other people, so it's not fair. But so they proved that star holds with, again, exponential decay for non-negative. So we're in the ergodic case, so xn is 1 over n z1 plus z2 to zn for zn non-negative or bounded.
So what are those options?
Just that the zn is stationary.
Would you remind me what that is?
Yeah, so stationary means that the distribution of any finite number of the variables is the same as the distribution of any shift of the variables. So if you take any k, then start from 1. So basically, there's no difference in the distribution when you change time. If you observe something at one time or at another time, you're not going to be able.
Any finite initial.
Yeah. So I'm taking consecutive ones, but you can just drop them out. And there's no, it's not necessary to assume ergodicity, but you can if you want. So if you're not from the theory of stationary processes, you should be thinking of a Markov chain. Of course, in the case of Markov chains, you get, or independent ones, you get explicit decay much stronger than this. So the point here is that it works for very general processes.
I don't quite understand this loop inequality, as you told us, implies convergence.
Yes.
Almost sure. And if you don't assume ergodicity, I could have sort of this probability 1/2 one limit, this probability 1/2 another limit.
That's true. For every sample, you're going to belong to some ergodic component, and you're going to, for that sample, well, for each ergodic component, you're going to get the same inequality, and then you're going to integrate, because this is a theorem about sample paths. So for each individual sample path, for each component, you get this, and then you just integrate.
Limit is almost a word constant. It's a limit.
Right. I haven't said anything about the limit. So the nicest, just I might mention that the nicest of these, the difference is in the techniques that they use. So this one is spectral. It's all about various operators in L2, and then they deduce it using some magic. And Ivanov has some combinatorial lemma about increasing real-valued functions, and he uses it. And Calico and Weiss use other combinatorial methods. And what I'm going to talk about is mainly based on an extension of their techniques. So their result has the advantage that it works for also random fields. If you want to look at processes indexed by lattice points and you want to average over squares, for instance, then it will work. But Ivanov has the best bound. Ivanov gets, so the probability that xn has k upcrossings decays of s and t is just is s over t to the k. So that's as aesthetically pleasing as you can want. And the other ones have other constants, but they get the same rate, essentially. I mean, no, they have worse constants. Okay, so...
They have worse constants, you said, but it's still s over t.
No, that's not true. It's worse, but it is exponential.
Okay.
It is exponential. And none of the new results work for L1. They only work for non-negative processes. This is somehow... Of course, you can't hope for exponential decay for L1. I think Bishop is tight.
What do you mean by for L1?
Sorry?
What do you mean by for
Cn
L1?
and L.
Just L1 without any assumption about positivity.
So that Bishop
Oh,
result
okay.
Cn is in L1.
Yeah, here you can have any integrable function. Here you either work with non-negative or bounded functions, which is worse. You can always... Obviously, it doesn't matter if you shift the process up or down by a constant. So...
It's either bounded or non-negative.
yeah. The bounded follows from the non-negative. You can simply add a constant to the process. It's not going to change the behavior.
So
It might
are
change the
there
constants a little bit.
examples, of things that are in L1 but not bounded below, but not non-negative, where you don't have exponential convergence? In other words,
Yeah, I'm pretty sure that Bishop is tight. I wouldn't swear, but it's not. I don't think it's in Bishop's paper, but there's a later paper which I'll mention. Well, there's a paper by. This is somewhat obscure, and I only learned about it the other week, by Michael Kravchak. From the Ergodic Theory Dynamical Systems journal in mid-80s. in 85. And what he does is he gets, he proves that if, so I'd rather not formulate it now. I'll formulate something sooner or later. He proves the subadditive ergodic theorem for L1 functions, and he gets the same bound as Bishop does. And he proves that it's tight. So, as I said, I just learned about this paper last week, so I'm not quite, I don't swear, but it should be tight. Okay, so what I'm going to tell you about is, as I said, an extension of Calico and Weiss's work. And the point was that we were trying to get, well, what I wanted was something like this, but that has to do with entropy. And we have convergence theorems for several convergence theorems which hold very generally and have to do with entropy, but none of them are effective. And what turns out, and you would expect that there is such a thing because the theorems about entropy, so let me formulate one. This is the Shannon-Macmillan-Breeman theorem, which says that if xn is a finite valued process, stationary, then if you look at the information function minus 1 over n log of the information, log of the probability of the observed sample. So this denotes, you look at the output that you got, you have n letters, and that defines, there's some probability that this occurred, right? So you plug that in, this converges almost surely. And the limit is going to be the entropy of the component in the ergodic decomposition that the sample belongs to, but I'm not actually going to talk about that. I'm only interested in the existence of the limit and what we can say about how it converges. And this is proved, there are several ways to prove it, but it's proved using the ergodic theorem and using martingales. And since we have these upcrossing inequalities for them, you would think that you can somehow deduce one for this, but that doesn't seem to work. It's hard to combine upcrossing inequalities in an effective way. It may be possible to do it. I don't know. So anyway, so let me formulate a result for this. So in fact, what we can add now is that the probability that this sequence minus 1 over n log of px1 to xn. So this is a sequence, as you observe more and more of the outputs, you get a sequence of numbers, and it's non-negative. So the probability that this crosses some interval st k times decays exponentially for some constants, and the constants depend on s and t and the size of the alphabet of the outputs of the process. So
wait, now this part is your result, or this?
Yeah, this is the new one. This is new. And rho similarly depends on the same parameters.
Number of symbols.
Right. So we said that xn is a finite valued process, and you have to take that into account. If you have too many symbols, then you can't. I don't know if it's not true, but I can't prove it.
So when you say finite value, so you mean has a finite set of values.
That's right.
It's not bounded.
It's not bounded, but in fact, I don't have to assume, I'm not using the values in any way except for to estimate their probability. So it's interpreting them.
If the number of finite values is n, then p of x1 to xn is 1, right? That's what you mean. I thought the other way.
No, I'm sorry.
5 values, then the probability of having 5 values is 1.
No. Okay. So suppose that, let's give an example. This is,
This is P of x1 after
set of values. Just this sequence of
So-
values, one is the
Suppose that xn is heads or tails with probability 1/3 and 2/3. Okay? You can ask, and it's independent, it's IID. So you can ask, what is the probability of observing heads, heads, tails? In this sequence in this order. Now here, so this is going to be 1/3 times 1/3 times 2/3. And it's different for a different sequence because it's not a fair coin. And here what we're doing is, this is a random sequence. We look at what came out, and we plug it in, and we get a probability exactly like here.
I don't understand, but you have a probability. I mean, this seems to be a number.
Yeah.
And now
But it's a random variable, this.
When you
Well,
say
so
number-
why is it a random variable? That I don't understand.
Because the outputs are random. Because I'm observing.
He's just looking at
Oh,
the coins.
he
It
looks
didn't
at-
come out to be, I mean, it's not, obviously not always going to connect. It's the outcome
Oh,
of
that's
flipping.
confusing. Okay.
Yes.
Yeah, it's a strange notation, but writing it in.
Yeah,
So what
that
is
is
P
a
of
weird,
X1
P
up
of
to
something
Xn?
is a weird notation for
P of
a random
x1 up to
variable.
xn is what?
P of x1 to xn. So okay, so let's write this.
But I think that's what's confusing people is that P doesn't sound like the name of a random variable to a lot
That's
of
true.
people. P of something does. It may be standard, but it
Well,
doesn't sound like it.
It is in some places, and it's obviously not in others. So, so this is a random variable whose value at omega
Random variable.
is the probability that of the event of all etas, such that x eta I equals x omega I for I equals 1 to n.
What is the first thing? It's a set of all etas, right?
All etas in our probability space.
Such that was actually this outcome.
It's an order sequence. And I say,
If you make another independent pick of y1 to yn of the same distribution, what's the chance you'll get what you observed in this
Right.
experiment, x1 to x?
So this is a slightly, this depends not upon, I mean, okay, I understand. x1 up to xn is sort of, you can't put the x2 and x5, and I mean, you really have to put x1 up to xn.
it's an order.
For the theorem, you certainly do. I mean, you can define this for any sample on any set of coordinates.
And the number of symbols will be, the coin is 2. It's not 2 to the third.
Exactly.
That's what you mean.
Exactly. So the number of symbols here is 2. And it works for any finite number, but the constants that you get do depend, in principle, on the number. They actually do depend on the number. That's not negotiable. I mean, the fact that, so what does the theorem say in this case, without the upcrossings, just the convergence? It says that if you look at a long, typical sample, in fact, for any sample, if you look at enough symbols, the probability of that word, not as a random variable, you've already fixed the sample, but you look at the output, the probability is very close to this. Okay, so it turns out the probability is close to h of 1/3 to the power of k. Probability of x1 to xk, where this is minus 1/3 log of 1/3. Oh yeah, so yeah, times some constant. No, this is sorry. 2 to the power of h of 1/3. Okay. Where hk is the entropy of 1/3. So 2/3 log 2/3. There's a, yeah. Okay, so it's saying that for long typical samples, each sample may have a different probability because they're not all the same. But for a typical long sample, you know that the probability of that sample will be approximately, it will decay exponentially, and the rate of decay will be this number. If for general processes, the expression for this is a little bit more complicated. Instead of h of 1/3, here we have an IID process with 1/3 and 2/3.
This is the simplest case. If we have 1/2, 1/2.
Then they're all the same, right? Then every sample has 2 to the minus k. Yeah.
Boom. It's just done. That's
Then the probability is just the same
It's all this, yeah.
for all.
Right.
Okay.
And this will come out, if you plug in 1/2 instead of 1/3, this will come out just 1.
There's no, I mean, it's just constant.
Yeah. And so you'll get what you should get. But in general, you can have events that are more probable and less probable. When you look at the output, you may see fluctuations of this probability, but in the limit, it will converge as it should.
And it'll do so exponentially in the length of the sequence that you
Yeah.
look at.
Except for periodic processes, but I mean, except for trivial exceptions.
So wait, you're sort of sneakingly getting in here some large deviations.
Well, for IID, there's a connection between entropy and, so this is the entropy in this case of the process. There's a connection between entropy and large
Well, but
deviations.
even if we didn't know entropy, sort of, if this crosses sort of not too often, then it means it must converge, as you told us before. That
Yeah.
looks like a large deviation.
If you come from ergodic theory, you think of it the way he does. If you come from mathematical physics, you think of it as large deviations. I mean,
Yeah.
I don't, but they're,
Although this isn't a large, I mean, for IID, you could maybe go both ways. I mean, if you know a large deviations result, then you might get something like this. The point is that this works for processes which have no independence. This works very, very, very generally for any process. It doesn't have to be IID, it doesn't have to be Markov, it doesn't have to be a Gibbs anything. It always works. And the constants don't depend on the process. That's the main point here. So like the Martingale theorem, right, like the ergodic theorem, the Shannon-Macmillan-Breeman theorem can be deduced in special cases from numerical estimates, not numerical, from explicit estimates on these probabilities. In general, though, you don't have any rates of convergence, but it's still true.
So my question was the other way around. Is it true that that theorem implies a large deviation principle? It sort of looks
This one, that the limit exists.
but
No.
it doesn't tell you
No.
anything about the rate, and large deviations usually tells you about the rate. Maybe yours implies.
Not either, I think. It's not.
The sequence could stay far from the limit for a very long time, and there can be no bound on how long, but it can't go up and down many times. So large deviations will tell you after some specified time, right, you know you're not too far from the limit, right, some estimate. But upcrossing inequalities don't tell you that. And in this general setting, it's impossible. All you can say is that you don't go up and down many times, but you could stay far away from a time that you cannot bound a priori in this general. And then, after a very long time, you see some new feature of the system that you didn't see before, some very long range dependence, and the average settles to its final limit. But it can't go back and forth and unbound the company.
Okay, so anyway, this is just an application, which
So is it, I mean, it looks sort of stronger than just almost sure convergence, right?
Oh,
it is.
yeah.
As I said, well, it's equivalent to almost sure convergence if you allow the constants. No, I'm sorry. Okay, so if you just knew that it was bounded by something that goes to 0, that would be equivalent to almost sure convergence. The added information is A, that the decay is exponential, B, that it doesn't depend on the process. So it works for anything, except that it does depend on the process in the sense that it depends on the number of symbols. That's what you get here that you don't know here. Here you only know convergence.
Well, no, let me put it like that.
And you're gonna let him go.
Yeah. Before we had all of that, when we sort of had Dupes inequality and stuff like that, we just had sort of convergence of
Don't have
Process.
Dupes inequality for these quantities. This is not Martingale.
It's not Martingale. But you do have, no, you don't have anything. This is not covered by the other ones. What we knew before was martingales and time averages.
This could be a really horrendous looking process. This allows really pretty horrendous looking processes that you couldn't go near before without the SMP there.
You knew a lot about them, just not crossing inequalities.
Right, and the new stuff is that tells you about crossing, but yeah, it's very general. I mean, you gave a really simple example, but the point is that this applies to things which are absolutely not large scale.
Sure. Yeah. No. As I said, for this, you can just do it explicitly. You can calculate what happens. And you can also get this explicitly from a large class. I mean, anywhere that you have enough independence, you're going to be able to calculate it. But
we're going to run out of time.
Okay. Yeah. Let me. This is an application. Let me show you what it's based on. I'm not going to show any proofs, but it comes from sort of a. Well, maybe before I give you the overview of where it comes, let me give you one more application. So, as I said, so this application is for the subadditive ergodic theorem. So Michael Kravchuk did it for L1, and that somehow didn't resonate. There's more, but
Didn't resonate with the community.
yeah, it somehow wasn't noticed, and then 10 years later, all these people published similar results for the ergodic theorem with exponential tails and exponential decay, and it did catch on. So there's he just published at a bad time. So what is the subadditive process? So I'll formulate it this way. Suppose we have xn is stationary and so stationary and r valued. It doesn't have to be r valued. And we have a function g which takes finite sequences of real valued numbers and let's say that it's r valued. Although that's not necessary. But we have a function that has the property that if you look at the value that it gives to some sequence a1 to am plus n, it's less than g of a1 to an time or plus g of an plus 1 to an plus m. So for instance, let's scratch the r value. It's some omega valued. And this is omega n. So suppose that omega is some set of linear transformations on some normed space, and then g of a1 to an could be the norm of the composition. And this is subadditive just because of I'm sorry?
Log.
Log, yeah.
Because of the plus, not right.
Yeah.
Plus, not.
Yeah, wrong side. So when you multiply matrices, the norm of the whole composition is at most the product of the if you break the composition into two blocks, and so with the log you get subadditivity. And so the theorem is that if G is bounded by M for some number, then the probability that doesn't have to be positive. The boundedness this time is from above, which is more useful. So G of x1 to xn, where this is again a sequence. You look at more and more outputs and you apply your function g, it crosses st k times, probability of this event is bounded by c rho to the k, where again c and rho depend only on m, s, and t. And what Grafchuk did was to show this for, instead of assuming that G is bounded, you assume that G of x1 is an L1. And then you get, rather than exponential, you get polynomial decay. So this, especially, maybe I should, another example of such a G is simply averages. You get this implies the ergodic theorem, for example, because, so here's another example. G of A1 to AN could be 1 over n, A1 plus A2. Yeah. Thanks. That will be implied by this once you know that G of one symbol. No, you're right. G of one symbol needs to be bounded. It's equivalent. It's equivalent. Oh, no, I'm sorry, it's not. Yeah.
Of n symbols, it's bounded by n times n.
Right, and that's
Right.
why you said either way.
Okay, so both of these, how much time do I have?
Half an hour?
Oh, plenty. Okay, so still feel free to interrupt, because that's plenty of time.
You don't have to
You
take the
don't
whole
have
time,
to.
but because,
That's an upper bound.
right, that's an over.
Exponentially.
I thought it was decaying much faster. Yeah. Okay, so both of these follow from a sort of maximal type theorem. It's not a maximal theorem, but it sort of looks that way. So let me give a little bit of notation. So I'll write I and j, semicolon, is the integer segment from I to j. And if we have a segment I, and a collection of subsegments I, ij in I, disjoint, then, and epsilon is positive, then the collection I of j, epsilon fills I if basically they cover all of I except for an epsilon fraction. So the union of ij is at least 1 minus epsilon the size of I. Right, so this is what it looks like. You have just, this is I, these are the ij's, and you allow a little bit of space not to be covered, but not too much, at most epsilon of the whole thing. So now, the setup that I want to look at is, so in both of these cases, what we're looking at are functions of samples of stationary processes. So we have a function g. So we fix some alphabet, let's call it sigma, in this case, or omega. Omega is going to be the output space of the process. We fix omega. We let g be a function from finite sequences of omega. And formally, it's also going to be a function of the space of stationary omega valued processes. And you should think of g as being the function that we apply to the sequence of outputs, and we get a number. So this is a function from here to the reals. And this second coordinate is in there so that we can, right, here it's not really a function of the sample. Here we depend on the distribution of the process, so it's not really empirical. Right here, for the ergodic theorem, it's really just the sample that we're looking at, but there we do need to know what P is. So formally I'm looking at something which takes a sample and knows what the process is, and it gives me a number. And so, okay, so the main technical result that you can use to prove both this theorem and the theorem that I erased is this. So you look at, you have G. If G is a function like that, and we have omega is the values that the process takes, and we have two numbers, s and t, and a parameter delta, which, well, you'll see how it comes in. In applications, we'll optimize over delta and it will go away.
When you say G as before, there are lots of G's.
Sorry, right, so G is from omega, from the union of omega to the n, times what it was supposed to be 2r. I'm not assuming anything about it right now, but G will come into the rest of the theorem. So there exist constants C and rho less than 1, between 0 and 1, which depend on S and T and delta, but don't depend on G. Such that for every stationary omega valued process xn, the following holds. That the probability that the sequence G of x1 to xn from 1 to infinity crosses st k times is bounded by two terms. One is 0 to the k, so this one decays exponentially, and the other one is frightening. So this is the probability that for some n greater than k, the segment from 1 to n can be delta covered by some segments I1 to Im, such that, so one condition is that Im is greater than k, it's at least k. K is this number over here. And G of x1 to xn is greater than t, and G of xa plus 1 to xb is less than s when for every ij, let's call this maybe aj and bj. Ij is the segment from AJ to BJ. Right, so what does this mean? There's a two-factor. What this means is that this is the probability that you're looking at some big sample, x1, x2, xn, and when you apply g to this sample, you get more than t. And then you break it up into small samples, which cover almost all of this, and when you apply g to each of these samples, you get less than s. So, okay, questions maybe.
So subadditivity tells you that
it's empty, essentially. Subadditivity will tell you that if you choose delta correctly, this is going to be empty, an empty event, and then you only get this term. Because what subadditivity tells you that if these guys are smaller, if g apply the average g, okay, so suppose that this is maybe.
So this g, just to relate it, this g is like 1 over n times g in the previous.
Yeah, it's a bit confusing.
So what were
You
you
also
going
need
to say?
boundedness,
So-
right? You also need boundedness along subadditivity to make the claim that it's zero. Second term is negligible, because otherwise you have delta fraction which can allow you to jump from s to t. So you need the boundedness of g to allow you to conclude that subadditivity is going to be zero. Second term.
That's in applying this theorem to the
Yeah,
subadditive case.
So here I haven't said anything about g, but of course this whole huge thing depends on g very strongly. So when you want to prove something more specific, what you have to verify is that how fast this thing decays.
So why in the subadditive, bounded subadditive case is this not going to happen? Because
If the interval is completely filled 1 n, then it follows just from the definition of subadditivity that you can't have that. And then because he assumed that g on individual symbols is bounded, the small delta part can't go too much.
can't ramp it up enough to, okay, fine.
I mean, the best example to think about is just averaging, maybe not even subadditive. If you have this whole thing is greater than t on average, the sum of everyone is greater than t, and the sum of these small guys on average is less than s, then this can happen only if you have negative values, big negative values on this small epsilon part, because it only has it switched around now because
Just in the formulation there, if g is averaging, then the only way that's possible
Is
is
if there are
there
huge
are
values.
positive values on the.
Right, because how do
Right,
you
I'm
get
sorry,
g
I'm
above
sorry.
t with
Right.
the little ones being small?
Yeah.
It's possible.
exactly. Okay, so not going to say anything about the proof except that it's constructive. I mean, and it's based on some combinatorics involving collections of segments. You can many theorems in ergodic theory can be proved by transferring this probabilistic question to a combinatorial problem, and then you apply sort of either things like the Vitali lemma or the Basikovich lemma or some sort of lemma like that. You get to some big collection of segments, and you get this sort of inequality. That's exactly how the maximal inequality in ergodic theory works if you know it, and you use the same sort of techniques here. So let me tell you one other application. Or theorem. So suppose that you have a 0, 1 valued process. Stationary process. And so let k of x1 to xn be the Kolmogorov complexity. What that means is this is the minimal n such that there exists some program.
N is already taken.
N is taken. Okay, thanks. So m. This is the minimal m so that for some computer program, so we fix our programming language, right? Or fix a Turing machine if you're a theoretical computer scientist. And this is the smallest program of length m. This is the smallest m, so there's a program of length m so that m outputs x1 to xn. Right, so this is a measure of how complex the sequence is. If you have a sequence of n zeros, if you have a sequence of n zeros, then in order to output n zeros, you need to tell what n is, and that's all. So you basically need a program of length log n. If you have a very random sequence, you're not going to be able to compress it very much in any way. Just by a counting argument up to constants, you're not going to be able to compress it at all. You can't have, right, the average length of, you just count computer programs, you can't have less than 2 to the n programs of length less than n if you're going to output 2 to the n different outputs, which is all the possible sequences that appear. And so what you can show is that, so we have our 0, 1 valued stationary process, and we have so I should say this is empirical. This doesn't depend on the distribution of the process, but it's not computable, unfortunately.
Now, when you talk about Kolmogorov, does it only make sense in the discrete setting, or
for finite valued processes, you mean? I'm sure people have generalized it, but
Discuss, you want to approximate within epsilon, so you have another parameter. You haven't finished stating the theorem.
I know. I'll get there. Okay, so the theorem is that the probability that 1 over n k of x1 to xn, this sequence, and you know the rest, crosses st k times, this probability decays exponentially. And in fact, so this is new. What's known since the early 1980s is that this is a paper by Brudno, that 1 over n k of x1 to xn converges almost surely to the entropy of the process. So this is the same entropy that I mentioned before, but it's not so important what the limit is. So it's, well, I should say the entropy of the ergodic component. But never mind what this is. It just converges to something. Okay, I think...
Case of the Sabbath theorem?
Well, it's almost subadditive. I'm not sure if you can actually deduce it from... Because so it's almost subadditive because if you want to write a program that outputs some big sequence, and you have a program that outputs the first half and the second half, then you just basically concatenate the programs and add a prefix saying first run the first program, then run the second program, and you get both. But there's some overhead, right? So k of x1 to xm plus n is at most k of x1 to xn plus k of x2 to xm. I'm sorry, to xn plus 1 to xn plus m plus, I don't know, maybe log of n plus log of m up to constants, where these represent the information that the extra information that you need to encode in the composite program, saying where the first program ends, where the second one begins, and that sort of stuff. So it's not precisely subadditive. I'm not sure whether you can...
But when you divide through by n and m, which you're about to do, then doesn't it, don't those extra terms?
It looks like it does. It looks like it does, but
Okay, so in other words,
it's not
K
so...
X1 constant plus plus the large constant times log n will be select.
Yeah, I guess that's probably true. Yeah, okay, so it's a special, you can derive it from Kingman's theorem. Yeah, okay, so I
You
think
don't
I'll
have to
finish.
use up the time. We just didn't want to talk so much and then tell you you're not allowed to finish.
Well, you can ask more questions, or you can just